We're going to look at approximating a derivative. So suppose you maybe have a table of values, or you have a graph with a couple of different values, and they say to approximate, what's the approximate slope of the tangent line, or what's the approximate instantaneous rate of change, or what's the approximate slope of the tangent line. Wait, did I say that already? Was approximation of the derivative. Those all mean the same thing. And you can, I guess remember that the derivative is the slope of the tangent line for the function. That's what I was just saying. So you can approximate it with the slope of the secant line. So what the heck does that mean? Well, we talked about the secant line slope already. But let's take a look at a general situation. So perhaps I have this this function, and I have x1, x2, and x3. Those are x values. They have their corresponding y values. And I say, approximate the slope at x equals 2. So I'm looking to approximate some slope of some tangent line like this. And there's three different things that I could do. So one thing is I can find the slope between these 2 points, the slope of the secant line there, because look at that. That slope is very similar to that slope. I'm drawing it poorly, but hopefully you can understand what I'm saying. So instead of finding the instantaneous rate of change there, I can find the average rate of change between those 2 points. That's finding the slope around the point in question. Or another approximation would be like finding the slope between these 2 points, because that, if these two are close enough, that is also an approximation for that slope. Or lastly, you can find the slope between those 2 points, which is still an approximation for that slope. This slope will be less steep than this slope, which would be less steep than that slope. So the order is actually important. I think we had a question like this on some review. And it was a good one. You're supposed to put them in order, like which approximation was what. I think there's something like with 29 point something and 31, or maybe you remember. But this slope would be the smallest. The instantaneous, would be the middle one, and the last one, the slope around the like after the point, is the largest one in this particular case. Because you could have different functions that make it different. So you maybe look at the graph. Definitely, if you have a graph, or if you can use a graphing calculator. I guess if you had a graphing calculator, then you wouldn't need to approximate. But so those are the three ways to approximate the derivative, and it's just using the slope of the secant line formula. So that's what I was talking about right here. The first method is to find the slope between x3 and x1. That's around the point. I'm finding that secant, and then secant slope. Method 2 is to find the slope of the secant line before the point, so right before, and then method 3 is the slope afterwards. So you can do each of those. Those are all valid approximations, and it's important to know when you are approximating, is it an under approximation or an over approximation? If you have something that's concave up, then we'll have it like we had before, where the first one is an under approximation, second one is exact, and the third one, method 3, would be an over approximation. If it was concave down, then it would change. Or like, if it, maybe it would change. I think it would change. So, there you have it. Now moving on to inverses. Something very, very important is the inverse formula, but also to know that the slope of f of x and the slope of its inverse, those are just reciprocals of one another. And hopefully that makes sense if you remember what an inverse function is. If you have something that, say it's like this, the inverse is just that reflected across the line y equals x. So it looks like that. So what we're saying is the slope, say the slope here, for the corresponding slope on the inverse, it's just going to be, well, that actually looks kind of the same, so I'm going to change it a little bit. Let's do it down here. So that slope is going to be the reciprocal of that slope. Hopefully that makes sense. So what does that mean? That means if I have the derivative of this, which means I have the slope of this at some certain point, like f prime of a, that's some derivative at some slope, then that would be, well, it's f prime of a. And then the reciprocal, I guess, f inverse prime of f of a. What? You get what? This is crazy. That equals 1 over f prime of a. So that might be a little bit confusing, but all I'm saying is the slope here, if you want the slope of the derivative at a corresponding point for the inverse, you just flip it over. So like if the slope was 3 over 2, then the other one will be 2 over 3. You don't make it negative. That's for perpendicular slopes. So hopefully that makes sense. I'm going to move on. You may be able to find the inverse of the function explicitly if you switch and solve. That's when you make the f of x into a y, and then you switch the x's and y's, and you solve all over again. And that's how you get the inverse. Sometimes you can't do that very easily, so it's not worth it. You just use the formula, and hopefully we are familiar with this formula. So if f and g are inverses, then that's the formula that we can use. Also, a special note: if a and b, or sorry, a comma b is on the graph of f of x, then b comma a is on g of x. So like this is how we've written it before, but that's what I mean by f of a, because here, if I plug in a to f of x, I get b, right? Well, that means on g of x, I get b to be plugged in, which is f of a. That's what I was saying right here, because the x and y values switch when you're thinking of inverse functions. So I guess hopefully this is a little bit more understandable than what I was trying to say here, because I guess that definitely can be confusing. And that's it. Hopefully that makes sense. Good day, sir. And ladies and sirs? No. Ladies, sirs, sir, miss, misses, miss. Whatever. Goodbye.